This is Lab4 Oscillations by Gabe Rogers. Start us off. Our main objective is to observe the motion of the spring mass system, in which the mass swings in an arc while oscillating on a spring. And we'll be using Newton's laws of motions and the energy principles, especially the law of conservation of energy, to understand and predict the motion of the system. The equations we'll be using a lot is the position and velocity update formulas, the kinetic, gravitational, and spring energy equations, and then the energy equation we'll be using to define the total energy is E equals K plus gravitational plus spring potential energy. So in calculations, our initial condition is the mass is equal to 0.402 kilograms, the period is equal to 1.519 seconds, and the actual length of the spring is 0.7 meters. To find the spring coefficient, we said is equal to 4 pi squared times mass over the period squared, which gives us 6.84 Newton meters. And then to find the length of the spring, the relaxed state, we plug in L minus mg over k, which gives us 0.124 meters. For our tracker data, we'll be using the x and y values move as sinusoidal functions, and both components have the same period, which is 1.19 seconds. And they are inverted, the inverses of each other. For the coding portion, it's a lot of for this part of the coding, we're setting up the initial values, which the mass of the ball was 0.402 kilograms. We set up the initial position, which is negative 0.12, negative 0.623 meters, respectively, to the x and y components. We set up the timing, which is just the frame rate of the video that we used in tracker. Then we put in the gravitational force near the surface, the spring constant, which was 6.84, L naught, which is the relaxing length of the spring, which is 0.124. And then we put in the length of the spring as time passes, the L hat, and then we calculate for S, which is the magnitude of L minus L naught. And then below that, we have the kinetic, we have the code for the kinetic, gravitational, and spring energies, and then E is equal to the sum of all the energies combined. Continuing on to the code that is in the calculation loop, we see that we define all the initial energies as the energies from the previous section of code. And then we calculate the gravitational force, spring force, and the F net from both the spring and gravitational force. And then, as you see below, we have the velocity and position update formulas. And then we have the way we update the spring, which is L is the position of the ball minus the spring's position. It's a lot of repeat from earlier. We have the L hat, which is L over the magnitude of L, and S, which is the magnitude of L minus L naught. And then below we calculate the energy changes, and that's just updating the energy with the newest positions to find the energy at that period of time. So in our glow strip simulation, we found that the total energy change is 0, although the spring and although all the energies fluctuate, and the spring and gravitational potential energies are almost proportional to each other, just proportionally opposite. And then it's kind of cool. The simulation kind of shows that it almost makes a rectangle shape in the simulation with the way it oscillates with the spring. So what does this mean? The energy principle is satisfied because although the types of energy fluctuate, the total energy remain the same following the law of conservation of energy, which is the change in energy is 0. And then we also found that the periods in the x and y components are the same, which is t equals 1.519 seconds, as shown below. Thank you all.